Welcome back to Office Hours with Dr. Clark. So today we're going to deal with isomers and resonance. So this is an overlap of general chemistry and organic chemistry where when we're doing lower structures, we're taught early in our chemistry career to say, okay, so C2H6O, let's draw the, the different isomers, right? And typically we want no formal charges with our isomers. So another word for that is closed shell. Well, closed shell means you don't want anything to be less than the octets. Um, and then so here are the two isomers for C2H6, the ones that obey the octet rule, right? So we call these isomers. So these are isomers. So we have the same molecular formula but different atomic arrangement. So these are isomers. So depending on your Lewis structure, you can generate, especially in organic chemistry, you can generate many isomers. So for example, C2H4O2, if I use bond line structure, which would make drawing easier, and that's something that an organic chemistry student has to become familiar with. So your bond line, we don't draw in hydrogens unless they're connected to a non-carbon atom. And we put in all our non-carbon atoms, and we make sure we understand that there's a carbon at this point, there's a carbon here. So this is acetic acid or vinegar. So that's one isomer for that molecular formula, but then you have others. Yeah, several others actually. It's actually can be fun, trying to figure out what isomers actually work. So there's another, this is ethylene glycol or antifreeze. So two very popular chemicals here. And there's more we can draw in the form of a ring. So something you always want to practice when you're starting out with orgo is, okay, so if you see bond line structure, that's just you will in your textbooks and online practices, so draw on your hydrogen so that you're clear what you're dealing with. Right? So I drew the hydrogens here, but if I were to do strict bond line, there would be no hydrogens drawn in. And then here, there are two hydrogens here. So really good practice, draw your hydrogens in, especially when we're gonna move into resonance now. So with the resonance, we have to be clear what our Lewis structure is, a legitimate Lewis structure. And then when we're asked to do resonance, not every molecule can't do resonance. So resonance, we're looking at different electronic arrangements. Right? So what I mean is I have the same atomic arrangement. Let's take acetic acid, for example. I have the same atomic arrangement, but I'm going to move the electrons around because one rule of resonance is if you have a double bond and then you have a single bond and then you have an atom with lone pairs, those lone pairs can resonate. And we use these curly arrows to show how the electrons are moving. So lone pairs here. And electrons always move towards electronegative atoms or to positive charges. And so here we're going to have a double bond here between the oxygen and we're going to have a negative charge and a positive charge on the oxygen. And we can always tell oxygen has a positive charge when it has six bonded electrons and one lone pair. It's definitely going to be a positive charge. And then if it has three lone pairs and one bonded pair, it's going to be a negative charge. So these two are resonance forms. So notice I did not move any atoms around. So I can't call them isomers. It's not a reaction. So this double arrow doesn't mean it goes back and forth between the two, as far as the chemical transformation. It just means that we're showing that the combination of these two is the actual structure for our molecule. And we're showing that in negative, the lone pair and the double bond kind of the pi electrons, which is what the double bond is made of, pi and sigma electrons. The pi electrons can actually move. So we can have a double bond here, we can have it here. So there's this movement of pi electrons. So there are some rules in resonance that we have to think about. So there is where you have an allylic lone pair or charge. We saw an allylic lone pair here. So this lone pair is allylic because it's connected to an atom that is bonded through a single bond to a double bond. And then triple bonds can be allylic too. So here's another example where we have an allylic positive charge. So in this case, a double bond is going to move towards a positive charge. Creating a positive charge on this carbon. So keep in mind, positive charges don't move because positive charges imply a deficiency of electrons. Electrons are the species that move. Positive charges occur when electrons move away and create a deficit. So right now we only have, if you were to put in your hydrogens, we only have two hydrogens. So we have 6 electrons, and thus if less than an octet, the carbon will have a positive charge. So when we move the electrons towards it, now the octet for the carbon is filled because there are 8 electrons around it now, 2, 4, 6, 8. And now this carbon has a deficit. It has only 6 electrons. Right? So that's so allylic lone pair or charge. So we can show you the. So if we have a negative charge on the carbon, this implies that there's 2 hydrogens again, but then there's a lone pair. Right? So note the difference with the arrows here. So my arrow is going to start on the lone pair, collapse onto the bond, and then this double bond is going to break and create a negative charge or lone pair on the carbon. So it looks like, we just turn the molecule around, but we understand that that's not the case because if you measure the bond lengths, the single bond length here and double bond length, they're actually not single or double. They're actually the same exact length. And they're somewhere in between a single and a double bond. That's how we know resonance is legitimate. So if we do a hybrid, we can show that the double bond, the pi electrons aren't confined to either between, any 2 specific carbons. It floats between the two. We can do the same thing with positive charge. We can say, well, there's a partial positive on either carbon, meaning both carbons share the positive charge. It's not exclusive to one or the other. And we can do the same measurement and see that the bond length is somewhere in between a double and a single bond. So, other resonance that you're going to see is if we have a disparity in electronegativity, like a multiple bond, like take this molecule acetone. If we have a disparity in electronegativity, we can envision electrons kind of pooling onto the oxygen leaving the carbon deficient. Now, anytime we create new formal charges from a neutral molecule, this molecule is not a happy molecule. We prefer molecules to be neutral. That's more stable. But we allow this structure, even though carbon here has only 6 electrons, which carbon, never likes to have less than an octet. But since oxygen is more electronegative, we can understand how there's a more electron density around the oxygen versus the carbon. So that's another way we see resonance. And then we also see, resonance where what if we have a closed ring and we have a series of double bonds? These double bonds can alternate and we get a resonance form. And we see this with benzene compounds a lot, right? And that's why we draw the benzene compounds a lot. You'll see the circle because we're saying that the double bonds, the pi electrons are delocalized. So a key term with resonance is delocalization. Delocalization. So we're saying the electrons are delocalized. So electrons are spread about the molecule. And that gives stability. That's a big deal with resonance, is how can we spread electron charge around? So we have a pile of electron charge that tends to make the molecule less stable. Right? So here are some, examples of, resonance. And resonance, we're going to see in another video, is very powerful in organic chemistry, especially when we're looking at acids and bases. Some molecules are more acidic than others, and the reason is because their conjugate base is resonance stabilized. So we're going to end here for today. So we just briefly went over how we differentiate between resonance and isomers. So remember, isomers, we're looking at different electronic arrangements. So we have different molecules, whereas resonance, this is the same molecule. Same molecule, but different electron arrangements. A very key difference. And then resonance comes with these electron movements that sometimes create charges. So you have a negative hotspot, positive hotspots. Sometimes both resonance forms have the same charges, so they're equal in stability. Whereas this one up here, this one is more stable than that one because that one has charges. That one doesn't. And it's something about resonance. One last thing before we go is if I'm looking at a molecule, let's say the isocyanates molecule, there are a few resonance forms for isocyanates. And there's this one here. And there is this one here. And then you have another one where, excuse me, where you have nitrogen has a lone pair, oxygen has the triple bond. So this one is a 2 minus, that's 0, that's +1. We're not in love with that structure because it's way too many charges. This one has a -1 on the oxygen, this one has a -1 on the nitrogen. So which would be the most stable resonance form? So let's say A, B, and C, right? So isocyanate has a overall negative charge on it. Otherwise, we have an uneven number of electrons, which is really hard to do with structures when you have an odd number of electrons with a negative charge to care of that. So the one that's the most stable is this one. Actually, no, I'll take that back. The one that's the most stable, excuse me, is the one with a negative charge on the oxygen. Because electronegative atoms stabilize electrons better. So if I have a toss-up between, okay, the one with negative charge and oxygen and nitrogen, I'm going to choose the oxygen because that's more electronegatives. Okay. So that's a brief overview of resonance, and we'll see you next time.